Hi and welcome to this video on proofs, in particular proof by induction and proof by contradiction. This video is primarily aimed at students revising for their A-level maths and or further maths exam, as well as students preparing for or partaking in a STEM-based degree. If this is the first video from my collection that you are watching, you may want to take some time to watch my introductory video. This should give you a better idea of how to get the most out of these videos. Let's first take a look at induction. In proof by induction, you are considering some proposition which depends on some integer value n. You want to be able to show that if the proposition holds for some integer k, then it also holds for some integer k plus 1, and ultimately that it must be true for all integers greater than or equal to 1. So let's look at the general structure. Of a proof by induction. First of all, you take your proposition Pn and state what it is. So let Pn be the proposition that, in this case, Fn equals Gn for all n greater than or equal to 1. Then we look at the base cases. Normally there'll just be one base case, and this is basically looking at, does the proposition hold if n equals 1? So we'd look at the left hand side and then the right hand side of our proposition. So in this case we'd write that f1 equals whatever it equals, and g of 1 equals whatever. When we find that f1 actually equals to g1, we can imply that p1 holds true. If our proposition Pn contains n minus 1 and n minus 2, for example, we may also need the case n equals 2 as a base case, but in most cases you'll only need one base case, in which you'd use n equals 1 if you're looking at all integers greater than or equal to 1. Then we need to make an assumption. So let us assume that Pn is true for some n equal to k, i.e. we're saying that for some n equal to k, f of k equals g of k in this example. We would then want to do some sort of algebraic manipulation until we reach the result we want, which is that f of k plus 1 equals g of k plus 1. This is the statement of pk plus 1. So we'd be showing that pk plus 1 holds true. We then have a concluding statement to write. So in this we say that we have shown that if pk holds true, then pk plus 1 holds true. And since p1 is also true, we can conclude by the principle of mathematical induction, which is the proof we're doing, that Pn is true for all And that's what this symbol means for all n greater than or equal to 1. This concluding statement is something you have to learn and write at the end of each proof by induction that you complete, making it relevant to your question. So to summarise, we have to state our proposition, look at base cases, which is usually just n equals 1, state our assumption that Pn holds true for some integer k, we do some algebraic manipulation to reach that pk plus 1 holds, and then we can write our concluding statement. So let's move on to looking at an example. So in this question, I'm going to let Pm be the proposition that the sum from r equals 1 to n of 3r minus 2 equals n times 3n minus 1 all divided by 2. And this is for all n greater than or equal to 1. So let's first look at our base case. So let's consider if n was to equal 1. Then let's look at the left hand side. Here we get that 3 times 1, because n is just 1, minus 2, which is 1. Now let's look at the right hand side. We get 1, again because n is 1, times 3 times 1 minus 1, all divided by 2, and this does indeed equal 1. So therefore, because the left hand side and the right hand side are equal, we've just shown that P1 is true. Now we need to make our assumption, so let's assume that pk holds true, i.e. we are saying that the sum from r equals 1 to k, as n equals k, of 3r minus 2 equals k times 3k minus 1 all divided by 2. So now we want to have a look at what pk plus 1 is. So pk plus 1 is the summation from r equals 1 to k plus 1 of 3r minus 2. And we know that this is equal to the summation from r equals 1 to k of 3r minus 2 plus the extra term when r equals k plus 1. So this is equal to 3 lots of k plus 1 minus 2. Our assumption then tells us what this summation equals. So we know that this actually equals k times 3k minus 1 divided by 2. And then if we add on the simplified version of this bracket, we're adding 3k plus 1. Let's simplify this further. We get this is equal to a half times k times 3k minus 1 plus 2 times 3k plus 1, which is equal to a half times 3k squared minus k plus 6k plus 2. Simplifying further, we get this equals a half times 3k squared plus 5k plus 2. We can then factorise this. Together is equal a half times k plus 1 times 3k plus 2. And then note, this is actually of the form that we wanted. So this shows that pk plus 1 holds true. So all that is left is to write out our concluding statement. So this is that p1 is true. And if pk is true, then pk plus 1 is true. So using the principle of mathematical induction, Pn is true for all n greater than or equal to 1. That is, the sum from r equals 1 to n of 3r minus 2 equals a half times n times 3n minus 1 for all n greater than or equal to 1. The rest of this video will be spent looking at proof by contradiction. In a proof by contradiction, you want to start off with an assumption. You then want to go through a series of mathematical statements until one of them is obviously false, i.e. until you reach contradiction. This means that the assumption must be false. So let's take a look at an example. Here I would like to prove that root 2 is irrational. So I will start with the assumption that root 2 is rational. So if root 2 is rational, what does that mean? Well, it means that we can write root 2 is equal to a over b, as any rational number can be written as a fraction. And here we've got a and b are integers, and they do not equal 0. We also can assume that a over b is in its simplest form. So this means that both a and b cannot be even. So at least one is odd. Okay. So going back to our statement that root 2 equals a divided by b, this implies that 2 equals a squared over b squared, which we can rewrite as a squared equals 2 times b squared. So this means that the square of a must be even. As we can write a squared equals 2 lots of another square. And if a squared is even, it means that a is even. Because if a was an odd number and we squared it, it would be an odd number, so a is even. So if a number is even, it means we can write it in the form of 2 times another number. So that means a must equal 2 lots of some integer k. Going back to this line here, let's sub in for a. So if a squared equals 2b squared, as a equals 2k, this implies that 4k squared to equal 2b squared. And then we can obviously divide by 2, so we get that b squared equals 2k squared. But then this suggests that b squared is even, as b squared is equal to 2 times another square number. And if b squared is even, we know that b is even. But that means both a and b are even. But this can't be true. As if both a and b are even, a over b would not be in its simplest form, as we would be able to cancel 2 from both a and b. So this is our contradiction. Mathematicians like to use a lot of symbols, so when you reach a contradiction, different mathematicians put different signs to represent contradiction. I'm going to put this sign, meaning this is my contradiction. So we've reached this point, we've got a contradiction, and this means our assumption cannot be true. So our assumption that root 2 is a rational number is incorrect, so we have proved that root 2 is an irrational number. Some other proof by contradictions you could try yourself are that there is no greatest even integer, or that for all n, if n squared is odd, then n is also odd. Thank you for watching my video.